start. Good evening, everyone, and welcome to this 11th lecture in our 2-year series on History of Philosophy of Science in 20 Objects. The Museum of History of Science, Technology, and Medicine, from which our objects come, is 10 years old this year, and the scholarly group around it, devoted to history and philosophy of science, is 60 years old. So we thought a lecture series like this one would be a fine way to mark these anniversaries, and would also give us a chance to share our mania for our subject with you. Now, so far, the objects that we've shared in these lectures have been exciting because they're authentic examples of historically important classes of objects. So to name a few lectures from last year, the microscope, the air pump, the brain saw. Ours are the real thing, but you'd be hard-pressed to say that anything especially consequential was attached to those particular objects. In the last lecture and this lecture, it's different. These particular objects are important to the history of science. In the last lecture in December, we looked at the Newman Phillips machine, which is known to the wider world as the prototype of the MONIAC, the world's first economics computer. It modeled the national economy, the flow of money through the economy with the flow of water. You can check it out now in the foyer of the Leeds University Business School. But in the 1950s, it transformed the very notion of what an economic model could be and what it could do. In this lecture, we've got the X-ray camera that we're reliably informed was part of the investigations that in the 1930s, right here in Leeds, produced the very first X-ray photograph of DNA. That happened here. And to tell us about it, I'm delighted that we have Dr. Kersten and Helen, who's a visiting fellow in History and Philosophy of Science here at Leeds. He is literally the author of the book on the man behind the camera, William Astbury. It's called The Man in the Monkey Nut Coat, published with Oxford University Press. He'll explain the title in due course. And he'll be ably aided and abetted by Helen Piel, who is a postgraduate student in History and Philosophy of Science here. So please join me now in welcoming Kersten and Helen.
Well, thank you to Greg for that introduction there, and thank you for all coming along tonight. The first thing I want to check is, can you all hear me okay there? Yeah? Good. That's good. Now, Christmas and pantomime season are a long, long way behind us, but in keeping with the spirit of pantomime, you may have seen, as you were all taking your seats, I've been indulging in a little bit of audience participation in the form of these rather unusual spectacles that I've been handing out. Hopefully you've all got access to a pair. I would invite you, when you do get your hands on a pair, just to take a look through them at any of the lights in here tonight and see what you see. Because we're going to use the spectacles this evening to understand how the X-ray camera works and why it has, I think, such an important place in the history of science. In fact, why I think it puts Leeds on the international map. Now, if I was to throw to you the question, what is Leeds famous for, I'm sure we'd be met with a myriad of answers. A once mighty football team, humbled and now clawing its way back up, hopefully to glory. I want to share with you two answers to that question, and the first one comes from a very high-profile admirer of Leeds, because that is Mr. Matthew Barson. I believe the correct form of address is His Excellency Mr. Matthew Barson, because he's the United States ambassador to Great Britain, or rather he was until last week, I think, because, of course, there's a new pair of hands at the wheel in the White House, and unfortunately Mr. Barson is heading for home, I believe. But he gave an interview in one of the broadsheets a few years ago, and he talked about his love of Leeds. He'd been to visit the city, and he'd absolutely fallen in love with it. If you're interested, you can go to the BBC iPlayer. You'll hear him enthusing about Leeds when he was a guest castaway on Radio 4's Desert Island Discs. But in one of those interviews, he confessed that prior to actually visiting the city, the only thing he really knew about Leeds was that it was where, in 1970, the rock band The Who had played a concert just over the way at the Student Union that had become the stuff of rock legend. It became known as their Live at Leeds concert, and certainly I remember when I was working in the United States, if anybody asked where you were from, and you said Leeds, there was this instant look of recognition as their face lit up and said, oh yeah, The Who, live at Leeds. So that's commemorated with a blue plaque on the Student Union today. Staying on the theme of blue plaques and what Leeds is famous for the question setters of University Challenge, where, I don't know if you saw the recent Christmas run, but the University of Leeds alumni team had a storming run as they got through to the semi-finals. And en route, they tackled a round which featured 3 questions about famous people from Leeds who were immortalised with blue plaques. And one of those blue plaques in question featured a very famous Leeds camera, but sadly it wasn't this one. It was the camera used by this gentleman here, Louis Le Prince, who shot the first moving pictures down on Leeds Bridge. Now, I have no wish to question the assertion that moving pictures have had a big influence on our lives, but what I want to persuade you of this evening is that if the University Challenge question setters were ever to run another round on famous blue plaques in Leeds, they might want to include this camera. And certainly, if Mr. Barson was ever to visit Leeds, as I say, sadly not likely, much as I'd love to show him the Who's blue plaque over the way, without wishing to detract from the achievements of Messrs. Daltrey, Townsend, Entwistle and Moon, I'd like to take him about 2 seconds walk from the one for the Who and show him the one that you see there on the left, commemorating Sir William Bragg, who was the scientist who, together with his son, developed the technique by which the camera works. So that plaque sits on Parkinson Building. And then I'd take Mr. Barson up the road to Headingley, right across from the cricket ground, and show him the blue plaque on the house where Bragg's protege, William Astbury, lived. And it was Astbury who took the camera and applied it to the study of the structure of biological molecules. And in the process, he helped to pioneer, blaze the trail for a whole new science, molecular biology, the idea of understanding living systems in terms of the shape and structure of the molecules from which they're made. And as Greg said in his introduction, in the last lecture we heard about models, we heard about the Newlyn-Phillips machine. Well, we're going to stay on models tonight because molecular biology gave us what I think is probably one of the most famous models in the history of science, and you can see 2 examples of it here. The double helical structure of DNA. So what we have there are 2 chains of sugar and phosphorus twisting around each other, and up the centre, on this model you can see go these 4 different coloured compounds. They're called the bases, and it's those that carry the biological information, the information that determines whether we have blue eyes or brown eyes, fair hair, dark hair, no hair. And it's this double helix that explains the key thing that the molecule has to do if it's going to pass on biological information. It has to be able to make copies of itself. And it does that by these 2 strands peeling apart and making copies of themselves. And that's how the genetic information gets passed on from generation to generation. And the double helical structure was famously discovered by the 2 Cambridge scientists we see here on the left. James Watson, gazing up there, enraptured at his colleague Francis Crick in Cambridge. They published a famous paper, April 1953, describing their structure. 15 years later, Watson published his famous memoir, some might say infamous memoir, The Double Helix, describing that discovery. And for many people, this book by Watson has become the orthodox account of the origins of molecular biology. Well, tonight I want to give you an alternative account of the beginnings of molecular biology, one that takes us outside the Golden Triangle of Oxford, Cambridge and London, and brings the story right up here to Leeds. But, and en route, hopefully that's going to raise a couple of interesting philosophical questions, such as, what is a gene anyway? Is biology the same kind of science as physics? And what is actually going on in an experiment when scientists do an experiment? But before we launch into that, an apology. Because if any photography enthusiasts have come along tonight, lured here perhaps by the allure of seeing some very sophisticated optical equipment when they saw the title of the talk, they are at this moment probably feeling a certain sinking sense of disappointment when they are confronted by what appears to be little more than 2 lead boxes with one side missing. Well, there's a very good reason why they're made out of lead, and in order to explain why that is and the principle behind which they work, I'm going to hand over to Helen here. So Helen, if you'd like to take over. Thank you very much.
Thank you. Can you all hear me? Good. Well, as Kersten said, there's a good reason why this box is made of lead, and that is it doesn't use visible light to take pictures. It uses X-rays. And usually when we think of X-ray photography, we think of its uses in medicine. We think of we're going to the doctors at the hospital and they take an X-ray photograph to diagnose maybe broken bones or another kind of disease. And these pictures usually kind of look like this. This is one of the first X-ray pictures that was ever taken by Wilhelm Conrad Röntgen, who more or less accidentally discovered X-rays in 1895. Maybe smartly not of his own hand, but he took an X-ray picture of his wife's hand. And these pictures, what actually happens is the X-ray passes through the body because matter is more or less transparent to X-rays. But when X-rays hit denser objects, like in this instance, bone or the ring that Röntgen's wife was wearing, then these denser objects cast shadows on the photographic film. And this is what we are familiar with when we think of X-ray photography. Now, this camera that uses X-rays works on a slightly different principle, and for that we handed out these spectacles that you hopefully all looked through so far. But if you haven't, you can try again later or after the lecture. Now, if you have looked through them, you've seen all the colors of the rainbow. And this happens when light passes through the lenses, it gets scattered. Or the technical term that physicists use for this is light gets diffracted. Now, we have to do a slight detour to Germany before we come back to Leeds, to a team of physicists surrounding Max von Laue. His colleagues were Paul Knipping and Walter Friedrich, and they in 1912 discovered that this principle of diffraction that you can see through these spectacles also applies to X-rays, not only to visible light. They had set up an experiment in 1912, and we can see a schematic of how this experiment was set up here. And Kersten is going to talk a bit more in detail how it applies to the camera that we have here tonight. But simply speaking, we have Max von Laue and his team set up an X-ray source, which we can see here on the left. And the beam of X-rays was then passed through a collimator to focus it to a certain width, and then it hit a crystal. They were using crystals, copper sulfate originally. And all these red lines that seem to move out from the crystal to the right, these are the diffracted, the scattered X-ray beams. And they are scattered and diffracted in the crystal. And they have a photograph, or von Laue and his colleagues put a photographic film at the end to record to record this pattern. And we have a picture here of what these patterns look like when they are recorded on photographic film. This is not the original picture that von Laue and his colleagues saw, but it is similar. And we can see all these black spots that create a rather simple pattern. Now, von Laue had a theory about what this image meant, and he had the theory that indeed the effect was caused by X-ray diffraction when X-rays pass through crystals. And he knew that crystals have a rather a well-organized structure, and he thought that these two might be connected, but he couldn't quite put his finger on all of it. Still, the results were presented to the Bavarian Academy of Science in 1912, and that he couldn't quite explain everything shouldn't diminish the discovery. But it does bring us back to Yorkshire, and more precisely to William Bragg, an English physicist who he was born in Wigton in Cumbria. And quite incidentally, the current Chancellor of Leeds University, Lord Melville Bragg, does not only share his last name, but also his place of birth with William Bragg. And they are, in fact, distantly related. They are third cousins thrice removed. Now, William Bragg had studied physics at Cambridge University, but then taken up a position at the University of Adelaide in Australia, where he had gained a lot of knowledge in radioactivity and radiation, and had become world famous for his research. So that in 1908, the just established University of Leeds offered him the position of Cavendish Professor of Physics, and in 1909 he returned to England with his family. He took up residence just up the road in Headingley, so that his way to work in the morning would have taken him either past or maybe on a fine day through Woodhouse Moor to the University of Leeds. But it was actually while he was on holidays near Scarborough that he learned of Max von Laue's experiments that had been done in Munich. He was sent a letter by a friend of his, a Norwegian physicist, who had talked to von Laue and observed some of the research. And the Norwegian physicist quite or described the experiments and also the implications, because at that time there were two parties who were discussing what the exact nature of X-rays are. And William Bragg belonged to the people who believed that X-rays were particles, while Max von Laue and his team belonged to the to the people who believed that X-rays were waves. And von Laue's experiments had some implications because they hinted at the wave theory. So William Bragg and his son Lawrence Bragg discussed this letter and the implications. Lawrence Bragg had a first degree in mathematics from Adelaide University, but then followed in his father's footsteps and just finished a second degree in physics at the University of Cambridge. And he spent his holidays with his family on the Yorkshire coast. Now, they conducted a few experiments trying to see if maybe the particle theory did still hold, but these experiments failed. Still, when Lawrence went back to Cambridge after the summer, he had all these discussions, or he brought all these discussions with him and all these experiments, and he kept thinking about the experiments and the implications. It was when he was back in Cambridge that he essentially cracked the problem that von Laue hadn't been able to quite solve, which is that he realized these patterns created on the photographic film relate back to the 3D structure of atoms in the crystals. Now, crystals are special because the atoms and molecules in them are arranged very orderly, as we can see in this model up there. And let's see. And the critical insight that Lawrence had is that the X-ray beams, when they hit the crystal and hit the atoms in the crystal, they are diffracted in a sense that they are reflected off the atoms. And having just finished his physics course, he was, of course, familiar with the law of reflection, that the angle of incidence is equal to the angle of reflection, which we can see in this lower picture of the two. Now, if we think of the planes of atoms in the crystal as mirrors, we have to think of them as slightly transparent, so that only part of the X-ray is reflected off the first layer, and then the rest goes on to the next layer, and then on, like only two layers are reflected in this one. But what Lawrence then did is he combined his mathematical knowledge with his physics knowledge, and developed a formula, which we can see up here. And this formula, if you apply this, you can basically work back from a 2D image of these patterns and structures on the photographic film to the 3D structure of the atoms and molecules in the crystal. And this formula is known as Bragg's law, and one of the most important formulas in physics. Now, Lawrence's research was presented to the Cambridge Physical Society in November 1912, and he kept in touch with his father at Leeds as well. And William Bragg then accepted, after his son's insight, that indeed X-rays were waves and not particles, because that is the only way that you can explain these patterns. Now, they combined the theoretical insights of Lawrence with the experimental expertise of William, and William then built a new instrument which allowed for better measurement and preciser measurements, and this is the spectrometer. We can see William here next to it, but there's still a replica in the foyer of the physics department here at Leeds, if you want to take a look at it. Now, this spectrometer was finished in 1913, and Lawrence came up from Cambridge to Leeds, and father and son conducted a couple of experiments and analyses with different types of crystals, from the more mundane ones like salt to more exotic ones like diamond. And if you're interested, Dr. Chris Hammond has been part of a team that have put the Bragg's the notebook of the Braggs on the website of the university library. So if you want to take a look at a lot of columns of measurements, and also some handwritten notes of the conclusions that the Braggs came to, you can take a look. But this, Dr. Hammond was also present when blue plaque was revealed on the house where the Braggs were staying in that summer of 1912. But as Kersten has already said, you don't need to travel all the way to Scarborough if you want to see a blue plaque for the Braggs. There is the one outside Parkinson Building, and there's also a wooden board in the Brotherton Library that was revealed in the presence of Lawrence Bragg, whom we can see at the very left. That was 3 years after William Bragg had died, so he wasn't present. But Lawrence and William Bragg also received the Nobel Prize for Physics for this, this insight that they had and this combination of the theory and the technique that they developed, which they called X-ray crystallography. And the Nobel Prize that they were awarded was the 1915 Nobel Prize in Physics, and today it is the only father-son team that have been awarded a Nobel Prize. And X-ray crystallography has moved from physics to quite a variety of different areas of research, biology, chemistry, and others. And the Austrian scientist Max Perutz, who also won a Nobel Prize based on his work with X-ray crystallography in 1962, together with John Kendall, has summarized it as follows. X-ray crystallography has allowed us to understand why water boils at 100 degrees Celsius and methane at minus 161 degrees Celsius, why blood is red and grass is green, why diamond is hard and wax is soft, why graphite writes on paper and silk is strong, why glaciers flow and iron gets hard when you hammer it, how muscles contract and how sunlight makes plants grow. Indeed, the Mars rover on our little red neighbor, the planet, is equipped with X-ray crystallography equipment, and it can take samples and try to widen our knowledge on the world beyond our own planet. But the track record of X-ray crystallography on Earth is quite impressive as well. Next to Max Perutz's and John Kendall's Nobel Prize, there have in total been 28 Nobel Prizes been awarded for research that was based or included X-ray crystallography. And the most famous one is probably the one that Kersten has referred to earlier, awarded to James Watson, Francis Crick, and Horace Wilkins for the discovery of the double helical structure of DNA in 1962. And how the mystery unfolds further, Kersten is going to tell us.
Well, thank you for that. Thank you for that fantastic account there of X-ray crystallography, Helen. And as Helen said, of course, 28 Nobel Prizes have been won using X-ray crystallography. And yes, the most famous one is probably that earned by Watson, Crick, and Wilkins. But if you know the story, you'll know that they couldn't have done it without the help of not the actress Nicole Kidman, but rather the crystallographer Rosalind Franklin, who Kidman won an award for her portrayal of in a hit play that ran in London a couple of years ago. Made it onto the front cover of all the broadsheets. The play was called Photo 51, and Photo 51 was the name of a very famous X-ray diffraction photograph of DNA that was taken by Franklin and her PhD student Raymond Gosling in 1952. I hope you can make out on the picture there that very striking cross pattern formed by the black spots. So, as Helen explained there, these patterns are formed by the scattered X-rays, in this case as they're passing through the DNA. Now, if you walk down the Strand in London, outside King's College, where Franklin and Gosling did their work, you'll see a plaque that hails Photo 51 as one of the most important photographs in the world. Praise indeed. It certainly got James Watson very excited when he was shown it for the first time. Because if you read his memoir, The Double Helix, he says, when he was shown that picture, my mouth fell open and my pulse began to race. Why was he so excited? Well, he knew that only a molecule that was twisted into a helix would scatter the X-rays to give you that very telling black cross pattern of spots. So Photo 51 was a very important clue for him and Crick. It's important to point out it wasn't the only important clue. They needed other crystallographic data from Franklin, numerical data which told them that the molecule was 2 chains, not 1, and that these chains ran in opposite directions. But Photo 51 certainly had a very psychologically important effect. It galvanized them, it spurred them into action. But what intrigues me is that actually neither Franklin, nor Gosling, nor Watson, nor Crick, nor Maurice Wilkins, none of them were the first people to see that all-telling cross pattern, because a year earlier, 1951, someone else had taken an almost identical picture, and that's a story that not many people know about. And that someone else was a research assistant called Alwyn Beaton, who was working with William Astbury up here in Leeds. And by this time, Astbury was a renowned world authority on using X-rays to study biological molecules like DNA. But if anyone had told him, as we see him there, as a young officer in the Royal Army Medical Corps in 1917, if anybody told him then that one day his fame and fortune would come to rest on X-rays, he would probably have laughed in disbelief, because at that point in his life, X-rays had brought him nothing but grief. He'd gone to Cambridge as an undergraduate in 1917, but of course the First World War was on, so he joined the army. Didn't get posted to the Western Front on account of a dodgy appendix. He was sent instead to Ireland. Not that Ireland was a bed of roses, because the year earlier they'd had the Easter Rising. Probably on account of his study in physics, he was put in charge of a mobile X-ray unit, because the military were one of the first organisations to really grasp the potential of X-rays. So he was put in charge of this X-ray unit, and later in life he used to like to boast that thanks to X-rays he'd earned the dubious military honour of getting not one but 2 court-martials. First time when a shelf with a load of X-ray plates collapsed, resulting in the loss of a large number of medical records. Second time when he repaired some faulty X-ray generator equipment with an old tin can and a bit of wire, which was not apparently appreciated by his superior officers. Well, X-rays may have been the bane of his military career. They were to be the making of his scientific one. After graduating, after the war finished, he went back to Cambridge, he finished his studies, graduated, and then he went to London, where he joined the team of William Bragg, because Bragg had left Leeds by this time. He'd come to London. Astbury joined him. In fact, in later years, Astbury would hail Bragg as being his scientific father, because it was from Bragg that Astbury learned X-ray crystallography. And Bragg set Astbury a new challenge, because until this time, the Braggs had just used X-ray crystallography to look at very simple crystals: diamond, ice, sodium chloride. Bragg had a new challenge in mind. Could X-ray crystallography tell us anything about the kind of compounds we find in living systems, biological molecules? And he had one very particular substance in mind. Now, at first sight, it wasn't a substance that was likely to set pulses racing. It didn't seem very exciting at all. It was the humble wool fibre. But there was a very strong practical reason for the interest there, because ever since the end of the 19th century, around about the start of the 20th, there had been this growing fear that Britain was going to be overtaken by economic rivals like Germany, and this needed to be addressed. And it was felt that what we really needed to do was to emulate the German example, do what the Germans were really good at doing, applying basic science to industry. And after his years in Yorkshire, Bragg had a very clear idea of one particular industry he thought could benefit massively from X-ray crystallography. That was wool and textiles. Because all begins really with Kirkstall Abbey down the road in 1152. Ever since the Cistercian monks there had been raising their sheep and selling their fleeces to foreign wool merchants, wool and textiles had been at the heart of certainly the Yorkshire economy, as we heard about in an earlier lecture in this series by Jamie Stark on the anthrax finger. And even today, the coat of arms of Leeds reflects the importance of textiles with the hanging fleece. So in 1928, Bragg sent Astbury up here to take up the post of lecturer in textile physics. And it wasn't a move about which he was particularly enthusiastic. In a letter to his friend and colleague, fellow pioneer of crystallography, J.D. Bernal, he said it left him feeling as if he was going into the wilderness. Well, how wrong he was to turn out to be. He came up here, he began using the camera that you see here to study the molecular structure of wool fibres, and it's worth just mentioning here just exactly what that involved. So, the camera here, as you see it, we direct an X-ray beam into it, and the X-rays are generated by a kind of glass tube. You'll see down here at the front. So we have a glass tube, we have a gas in there at low pressure, we apply a massive voltage across that glass tube, the tube gets incredibly hot, it's all very dangerous. You've got a really red-hot tube, massive voltages, and it's kicking out X-rays. And plus, you're doing all this in the dark, stumbling around doing it all. You direct your X-ray beam into the camera, and you've got your sample, your wool sample mounted in there. The wool sample has to be prepared. You can't just get a bit of wool off a sheep and chuck it in there. It has to be scoured. The grease has to be removed by treatment with alkali. In other words, there's a degree of manipulation going on there. We'll come back to that later. Okay? You direct your X-ray beam in there, and you leave it for 10 hours. It takes a 10-hour exposure. So this is not a quick business. Well, through that procedure, Astbury was able to answer an important question that had puzzled scientists for a long time, and that is, what is a protein? Now, you might think, why on earth is that important? A protein is surely just something in a big slab of meat that you have for your tea. The best way to understand it is to think that, we hear a lot about the importance of DNA. I said earlier, it carries biological information. What it's actually doing is, it's carrying the information in the form of these bases, these four coloured compounds that go up the inside of the double helix. It's carrying the information that tells a cell which proteins to make, because it's proteins that are the workhorses of living things. They're very much the Cinderella molecule of molecular biology, eclipsed by their cousin, their DNA. There are protein enzymes that catalyse chemical reactions. There are protein hormones like insulin, which we'll come back to later on. There's hemoglobin, protein that carries oxygen around the body. Rhodopsin, protein in the back of the eye that turns light energy into the energy of a nervous impulse. At the time Astbury was doing this work, though, nobody really knew chemically what a protein was. It was known that they were made of up to 20 of these smaller compounds called amino acids. You can see them all here. I sat up meticulously the other night building them all with my molecular Lego. They are the building blocks of proteins, but nobody had any idea how these come together to make a protein. It's rather like knowing that a house is made of bricks, but not having a clue how those bricks are arranged. And it had been proposed that maybe these different amino acid compounds physically join up together to make huge, great big long chains, rather like beads on a string. And sure enough, this is what Astbury's work on wool confirmed. He showed that the keratin proteins in wool were great big long chains of amino acids, or as he described it, rather like a molecular centipede. And what's more, they could do something interesting. They could change shape. They could take on a stretched out form or a compacted form. Now that was significant because it explained the key property of wool that made it so attractive as a raw material for the textile industry, its stretchiness. That was a milestone because you had an explanation of an everyday property in terms of a shape change at the molecular level. And for Astbury, that came to define the core idea at the heart of molecular biology, the idea that we can understand the living world by understanding the structure and shape of these giant chain molecules, DNA and protein, that make up living things. It was all summarised rather wittily by his mathematician colleague, Lindo Patterson, who said amino acids in chains are the cause, or so the X-ray explains, of the stretching of wool and its strength when you pull, and show why it shrinks when it rains. And I really hope he didn't give up the day job of being a mathematician. That put Astbury on the map. And he cast his net wider over his career. He looked at other protein chains like myosin in muscle fibres, bacterial flagella, so these are the whip-like structures that bacteria use to swim. He also noted that if you compared the molecular structure of the keratin proteins in reptile scales with the keratin proteins in bird feathers, they were remarkably similar. And he said this hinted at some close evolutionary relationship between birds and reptiles. Now, I think today we're all pretty familiar with the idea that birds evolved from dinosaurs, and it's quite routine to explore new evolutionary relationships at the molecular level by lining up DNA and protein sequences. I think Francis Crick first suggested that idea, that could be done in the 50s, but nearly a quarter of a century earlier we had Astbury suggesting just that you could tease out new taxonomic relationships down at the molecular level. But of course, proteins weren't the only biological fibre he was looking at. In 1938, his research assistant, Florence Bell, shown here on the left, took the first successful X-ray pictures of DNA. And you can see one of them there, and yeah, it just looks like a kind of smeary mass of spots. But from that, Bell and Astbury were able to propose the first model of what DNA might look like. So we're back to models. Now, they got several things wrong with their model. They thought the molecule was just one chain, not two. But something they got right was that the bases that we know today carry the information, stack up on top of each other, as they likened it, to a pile of pennies. And they were even able, from Bell's work, to measure the distance between adjacent bases, which James Watson later acknowledged gave him and Crick a very important foothold when they began building their own model. Excuse me. I think it's also worth pointing out what was important about this work was it showed that DNA had a regular, ordered structure that could be studied by X-ray analysis, and it laid the foundations, I think, of what came later by Franklin and Wilkins. Excuse me. It's also important to point out, today, there's rarely a week goes by we don't hear about DNA in the media, whether it's in crime shows like CSI being used in DNA fingerprinting, or in the news to identify the body of Richard III, or even more recently I heard about some London council who's going to set up a database of dog DNA with a view to naming and shaming irresponsible owners. A myriad of uses to which Watson and Crick and Astbury and Bell could probably never have envisaged their work would be put. So, yeah, we're all very familiar with DNA as being central to genetics. It was very different at the time they were doing this work. Not many scientists thought DNA was the genetic material. The smart money was on it being proteins. Why? Well, because, as I said earlier, proteins are made of up to 20 different amino acids. It seemed that their capacity for variation and to carry information must be much greater than boring old DNA, which is just made up of these 4 repeating bases. So DNA was thought to be little more than a structural molecule. As one writer put it, just a wooden stretcher behind the Rembrandt. Now, that began to change in 1944, thanks to the work of a gentleman here, Oswald Avery, who, if he was to know that in years later his work of 1944 would be placed on a par with the D-Day landings of June that year in terms of their importance in human history, I think he would have been flattered but bewildered. He was a very shy, retiring guy, not the kind of guy to blow his own trumpet. What did he do that was so important? Well, he showed that in bacteria, DNA could carry biological information. It could pass a biological trait between bacteria. It was very strong evidence that DNA was the genetic molecule. It didn't usher in an overnight revolution. It was met with a lot of scepticism. But one of the first people to really sit up and take notice of the importance of that work was Astbury here at Leeds. He described it as one of the most remarkable discoveries of our time. And he wrote to Avery, asking, would he please send some DNA for analysis? And Avery never replied. As I say, he was something of a recluse. But the real impact was Avery's work fired Astbury up with a dream. And that dream was that after World War II, he would establish the national centre for this new science of molecular biology here at Leeds. Sadly, not everybody shared that dream. The University Senate granted him permission to set up a new department with him as professorial head. What they didn't let him do, however, was to use the word molecular biology in the title. Some very bizarre and Byzantine academic politics intervened. Apparently there was resentment from certain biologists who got very territorial and objected to what they perceived as an encroachment by this outsider, this physicist coming in and encroaching their rightful intellectual turf. Interesting tension there between biology and physics. We'll come back shortly to that relationship. I always think it's vindication, if ever, of Henry Kissinger's observation that if the politics of academia seem so vicious, it's often because so precious little is at stake. Bless them, the University of Leeds did grant Astbury premises. They housed him in a former residential home in a terrace of Victorian houses that stood opposite the Student Union, where the Who have their plaque, but it was a far cry from what he'd hoped for. The floors were uneven, causing the scientific equipment to wobble. The electrics were dodgy. The plumbing was dodgy, leaving the place prone to flooding. It was not what you might have hoped for in a state-of-the-art research facility. And on top of that, as anybody out there who still works in scientific research will be all too aware, there's the ever-present problem of funding. And Astbury had been led to believe he could confidently approach the MRC, the Medical Research Council, and they'd back him. He went to London and they rejected him. And that was a blow to him. And that came at a time in his life when he was increasingly feeling disillusioned, feeling that he was beginning to, having ploughed the furrow, having really waved the banner for molecular biology, he was beginning to be marginalised and shoved out by people coming into the field. He soldiered on, though, and in 1951, his man Alwyn Beaton here on the far right there, took a new X-ray picture of DNA with the camera, and I hope you can make out it has that same striking cross pattern that we saw in Franklin's and Gosling's photo 51. The picture that set James Watson's pulse racing and his jaw dropping. And Watson's response is interesting because Astbury's response couldn't have been more different. His jaw didn't drop, his pulse didn't race, he did nothing with that picture, he never published it in a journal, he never presented it at a meeting. Now, we can distill an interesting point there from Astbury's reaction, or lack thereof. It tells us something. What do we need when we're doing science in the lab? Well, we maybe need 3 things. We need the equipment that gives us the data, but thirdly, shouldn't be forgotten, we need what's going on up here as well. We need concepts. We need the concepts through which we interpret the data. So look at that point another way. As I said, we understand today the importance of the double helical structure of DNA. It's the 3D shape of the 2 chains twisting around each other that allows the molecule to make copies of itself. But you know, as the science writer, broadcaster and professor of zoology at Manchester, Matthew Cobb, pointed out in an excellent book last year, actually, a crystal can copy itself. the really interesting thing, Matthew Cobb says, that DNA does is it carries the biological information in the first place. And for Cobb, Watson and Crick's most exciting paper was not the one in April 1953, where they came up with the double helix. It was the one that came 6 weeks after, where they hinted that the way the biological information is carried is in the order of these bases. So we have the 3D shape, allows the molecule to copy itself, but it's the 1D sequence of bases that carries the information. Now, Astbury knew none of that. For Astbury, molecular biology was always about the 3D shape. And so he would have had a very different interpretation, even if he'd solved Beaton's picture. Even if from Beaton's picture he deduced that DNA was a double helix, he would have had a very different reaction to Watson, because for Astbury, a helix would have been an outright disappointment. It would have just been a boring, monotonous, repetitive spiral, incapable of carrying any biological information. Well, I want to show you now an X-ray picture which did get him excited, so much so it's said to have brought tears to his eyes. It's here on the far right. It's an X-ray picture, taken with the camera there, of the keratin proteins in human hair, but no ordinary hair, because it came from a lock of hair that had come from Astbury's favourite composer, Mozart. The lock of hair is up in special collections. It's still up there. Astbury's other great passion, alongside molecular biology, was music. In fact, as he became more disillusioned, he often said he wished he'd spent more time playing his violin. It also provided him with a metaphor to talk about molecular biology. As he often said, the chain molecules, like proteins and DNA, are nature's chosen instrument in the symphony of creation. Excuse me. But it gave him more than a metaphor. Because if you came to Graham Gooday's lecture earlier in this series, you'll remember that beneath the surface of music is maths. And for Astbury, as a physicist, beneath the messy realities of the biological world, there also was maths. And this takes us to another interesting question, I think. Is physics the same kind of science as biology? Because Steve French raised the question, and he explored the topic in his earlier lecture in this series, about the science being a search for laws. And in physics we have laws like Newton's law of gravity, laws that we can express mathematically with nice, neat equations. The question is biology like that? Some might say, well, yeah, there are things like the laws discovered by the Augustinian friar Gregor Mendel, who's, if you look in the textbooks, they hail him as the founding father of genetics. Aside from the fact that historians and philosophers have long debated about whether what the textbooks tell us Mendel was doing is what he was actually doing, raises the question of whether Mendel's laws that he talks about describing genetics, are they of the same kind as Newton? Can they be expressed mathematically? Or have they like kind of a local rule of thumb that's been shaped by one particular trajectory of evolution? For Astbury, as a physicist, he was definitely convinced that with his camera there, he could uncover mathematical laws that described the formation of proteins, the way that amino acids are laid down to form proteins. But he also thought we could go further than just observing the structure of biological molecules. I think the best example of that is this cartoon on the left, appeared in the Yorkshire Evening Post, January 1944. It refers to a rather unusual overcoat that Astbury wore, and we'll see whether...
Perhaps you will allow me to tell you about my overcoat. I wore it on the way to this broadcast. It is made in part from fibres formed from a protein extracted from monkey nuts. It is what I may call...
There you go. We'll, sorry to butt in on the great man there. As he said, it's made from fibres made from monkey nuts. As we see here. So what had happened was, towards the end of the 30s, Astbury had done some work on seed proteins, and he'd shown by chemical treatment you could disentangle the chains of the seed proteins and refold them into insoluble fibres that it was hoped might make a cheap and abundant raw material for the textile industry that would substitute for wool. And ICI liked this idea, Imperial Chemical Industries. They liked the idea so much, they set up a pilot production plant in Scotland producing a textile fibre from monkey nut extracts. Now, as proof of principle, they made Astbury this entire overcoat out of monkey nuts. Well, sadly, the monkey nut fibre never proved to be the salvation of the British textile industry, but it did serve as a powerful symbol of Astbury's idea. Not only could you observe the structure of biological molecules, as with the cameras, we could deliberately manipulate them for our own practical ends. And he even said one day there'll be whole industries based on the manipulation of biological molecules. Well, sadly, he never lived long enough to see that come to fruition. He died in 1961. Following decade, it did come to fruition, albeit in a slightly different shape. And this is why Professor Herbert Boyer here is looking so chuffed with himself on the front of Time, because he's just become a very rich man, because he set up a biotech company, Genentech. And what the scientists at Genentech had done, they'd taken a chunk of DNA that tells a human cell how to make the protein hormone insulin, and with a bit of molecular spot welding, they joined it to DNA from a bacterium. So what you end up with is a bacterium that's then churning out bucket loads of human insulin. I have one other example of that kind of manipulation, but this isn't to make a practical product. This is actually an experiment. And so what you're seeing there on the left is, that's a human cell. It's a human kidney cell. And the researchers who were studying that were interested in a particular virus. So when a virus infects a cell, it injects its genetic material into the cell and hijacks the cell's own protein-making machinery for its own ends to start making its own proteins. The researchers there were interested in one particular virus protein. They wanted to know whereabouts in the cell does it go. Does it go to the nucleus, where the DNA sits? Does it go to the membranes? Does it swim around in the cytoplasmic jelly in between? To answer that question, they needed to make that protein visible so they could see it directly under the microscope. To do that, they did a rather clever trick, again involving manipulation. They took the chunk of DNA that carries the instructions for the virus protein, and they physically joined it to a chunk of DNA from a completely different organism, a jellyfish. And that particular set of instructions make a protein that glows in the dark when you shine UV light on it. So you've now got a recombinant DNA molecule, hybrid, part virus, part jellyfish DNA. Insert that into the kidney cell, and the kidney cell begins to use those instructions to make a hybrid protein. You've got your virus protein, and stuck to it, tagged to it, is this glow-in-the-dark jellyfish protein. And when you shine UV light on your cell, it lights up and you see where your protein's gone. It raises a question, however, and that is, to what degree have you manipulated your system there? How representative is that system you've created of what's really going on in nature? I said earlier that Astbury's experiments with the camera involved some degree of manipulation. This takes that manipulation to a whole new level, and I think it's something that the molecular biologist has to consider very carefully when they're designing their experiments. How representative is this really, or is it tipping over into complete artifice? That degree of manipulation raises another interesting question as well. What is a gene? We hear a lot in the media these days about the gene for. The media love this idea that the gene's a nice, discrete, particulate unit of heredity. So we hear talk of the gene for this, that and the other, the gene for criminality, the gene for violin playing. Philosophers of biology are beginning to challenge that idea. There was a book by one, Evelyn Fox Keller, a few years back, where she was suggesting that after a century of thinking about the gene like that, it's becoming a bit frayed at the edges through overuse. And what I find interesting is that Astbury had actually raised that question way back in the 30s. What is a gene? Is it a physical object, a material entity, or are we better off thinking about it as a set of interactions? Well, finally, we'll wrap up on a historical question. We've had two philosophical questions there. So, Astbury lived up in Headingley. The blue plaque's on his house at 189 Kirkstall Road, right over the road from the Len Hutton gates at the cricket ground, because the chances are, if you say the name Headingley to anyone today, they're not going to think of the first attempt to solve the structure of DNA. What they will think of is Test cricket, because that's what Headingley's known for, particularly the legendary performance of Sir Ian Botham in the 1981 Ashes series, when he snatched what seemed like inevitable... It seemed like snatched victory from the jaws of what seemed like inevitable defeat at the hands of Australia in the Ashes there. Now, the fact that someone like myself, who doesn't know very much about cricket, even I know about Botham's 8-1 Ashes, tells us how we write the history of sport. The history of sport is very much history of winners. It's a binary telling of history, winners and losers. And there's a tendency to write the history of science, I think, in a very similar way. Nowhere more so than in the DNA story, but I think, you know, what works for sport doesn't work for science. Because when you write the history of science like that, you tend to obscure the input of people like Astbury. And there's a good example of that. Just before Christmas, the eminent science writer Matt Ridley, author of books like Genome, wrote a really good, really entertaining gripping piece in the Times where he was talking up Britain's track record in life sciences. Thanks to Adrian Wilson, by the way, for flagging this one up. And he said this is thanks to our brilliant biologists. And one of the examples he wheeled out was cracking the DNA structure. But it's worth pointing out that in that particular example, as I hope you've realised tonight our brilliant biologists had more than a helping hand from our equally brilliant physicists. Usually when people think about physicists who got interested in biology, they think of this guy, Erwin Schrödinger. He wrote a little, he's usually remembered for being a founding father of quantum mechanics and coming up with a particularly tortuous and famous thought experiment involving a cat that's maybe neither dead or alive, and it's provided plenty of plot material for the writers of the sitcom Big Bang Theory. But in 1944, while he was in exile from the Nazis in Dublin, he wrote a little book, What is Life? And what he tried to do in that book was think about biology like a physicist. And so many other physicists since who got into biology, like Francis Crick, like Maurice Wilkins, have hailed that book as their road to Damascus, their epiphany. One molecular biologist said it was Uncle Tom's Cabin for molecular biology. He's citing the book by Harriet Beecher Stowe, which was against slavery and which is supposed to have helped propel the US towards civil war. Similarly, he was saying What is Life was a call to arms. Physicists, chemists, come with your techniques, bring them to biology and get stuck into biology. Well, I hope what you've learnt tonight is that well before Schrödinger wrote that book and indulged in all his theoretical speculations, we had our man here, William Astbury, not just indulging in theoretical speculations, but with the camera actually coming up with a positive experimental contribution to biology. And let's just give Astbury the last word on that.
These threads not only weave in and out through some of our greatest industries, but also, if you care to follow them further, lead straight to the heart of the mystery of life. It is a most adventurous and romantic field to explore with the X-rays, and I only wish that people who decry science because of the tragic way it has been abused could share the adventure and romance and see for themselves how wonderful are these triumphs of the peace of science.
So that was a great man. One final note, he didn't just blaze the trail in molecular biology with that camera. He didn't just blaze the trail in doing the founding works of DNA. He blazed the trail in another way, because he didn't just keep science into the lab. He was very keen at getting science out of the lab. So he would go and talk to lay audiences. He would talk to audiences of hairdressers and explain how molecular biology could account for why hair perms. And I nearly touched my head then when I was talking about hair, and I don't know why I did that. And as you heard him there, he was regularly on BBC Radio. So here we had a media-savvy physicist who was getting out there and bringing to ordinary people the excitement and adventure and romance of science. And in that respect, I like to think that he kind of blazed the trail for a rather famous heir when it comes to media-savvy physicists. And on that note, I will wrap up. Thank you all for coming along. There's a special thanks as well to Headingley Library for two reasons. Mrs. Munira Mohammed, who very kindly loaned me this model, and Mr. Bill Astbury, who's sitting up there, who's Astbury's grandson, who's been incredibly supportive, following a very random meeting in Headingley Library many, many years ago over a reading of the Gruffalo, that has been ever supportive ever since. And I just want to thank you very much for that, Bill, and thank you all for coming along and listening.
Thank you.